Assalamu alaikum. The lecture for today is buffer solution. We start with the definition, buffer equation, buffer capacity, buffer in biological system, and pharmaceutical buffer. We will define the meaning of buffer and what the meaning of buffer equation, capacity, and how we use the buffer in biological system. In addition, what's the importance or the significance of pharmaceutical buffer. Now we start with the definition. Buffers are a mixture of compounds that resist change in pH upon the addition of a small quantity of acid or base. That means we have a mixture of compounds, and when we add a small quantity of acid or base, there will be a small change in the pH. As you know, the buffer composed of weak acid or weak base, and we start with the next page, how we write the equation of buffer for weak acid and base. If we take now the equation for buffer for the weak acid and the salt of this weak acid will be, there is a common ion shared between them, it is AC minus. So the Ka, dissociation constant for a weak acid, is disturbed because the common ion supplied the salt and will increases the AC concentration as in this equation. So Ka equal to H multiplied by AC over the acid. And to re-establish the constant Ka, what we call the dissociation constant for the acid, is decreased by the shifting of equilibrium in the direction of the reactant. يعني راح يرجع عندنا التفاعل بالاتجاه الثاني حال زيادة ال H اللي يرجع يتحول إلى الأسيد and water. راح تكون المعادلة بهاي الطريقة، فراح يكون عندنا ال Ka in the forward reaction the AC will be increased, and by forward reaction the H what we call the hydronium ion will be decreased over the concentration of original acid. Since the weak acid is slightly ionized initial acid, since most of AC comes from the salt، راح يكون هو التحلل للسالت وراح ينتهي التركيز الأعلى بالنسبة لل AC. راح تكون معادلة بهاي الطريقة salt over acid by the hydronium ion by rearrangement the equation and using the logarithm from the pH equal to the pKa plus log salt over acid. The previous equation is known as the buffer equation. As we know, the name of Henderson-Hasselbalch equation for the weak acid and weak base. You can take a look for this equation, the pH equal to the pKa plus log salt over acid, and for the weak base it will be pH equal to the pKa plus log base over salt. We have here a question regarding the preparation of buffer solution not from the weak bases, and the reason is volatility and instability of the bases. This is the first reason we cannot use the bases in preparation of buffer solution, and the second reason is dependence of their pH on the pKw, which is often affected by temperature change. So if we want to take a look for the equation for the salt, we will see there is a pKw and it will be depend on both pH, pKa for the acid and for the base. Example, what is the pH of a buffer solution containing 0.1 molar acetic acid and 0.1 molar sodium acetate? The Ka for acetic acid we have 1.75 multiplied 10 to the power minus 5. So we have pKa equal to minus logarithm Ka. the pKa, it will be equal to 4.76. This you can take it from the using the antilog for in calculator, and you will get the pKa equal to 4.76. pH, it will be equal to the pKa plus log salt over acid, weak acid, because this equation related to the weak acid, and you can apply the numbers of acid and salt concentration in the equation, and you'll see here the pH is equal to the pKa in case of salt and acid having the same concentration. Another example, how much sodium acetate in mole should be added to 100 ml of 0.1 mole per liter acetic acid solution to prepare a buffer of pH 5.2, knowing that the pKa for acetic acid is equal to 4.76. So if you take a look in this equation, you have the acetic acid molar concentration, you have the pKa and the pH, and you will get here, after arranging the equation to get the salt concentration, it will be 2.754 mole per liter. We have here the number of mole, you should get it, so molarity equal to mole over the liter or volume, and will be in this form, number of moles of sodium acetate equal to the molar concentration multiplied by volume, and you see here the volume and the concentration, you will get the number of moles of sodium acetate. Another example, you can take a look here and you practice by using pKa for the ephedrine 0.1 molar and the ephedrine hydrochloride 0.01 molar. Here you got the value of Kb for ephedrine, and it will be 2.3 multiplied 10 to the power minus 5. And you apply on this equation, you will get the pKa equal to pKw minus pKb, and you will get the value for pKa, it will be 9.36 applied on the equation, and you have the concentration, the molar concentration of the salt of ephedrine hydrochloride, and for the ephedrine, and this equation for the base, in fact, so you will get the base over salt here, and you will get the pH is equal to the 10.36. We have here what we call the pH scale. From 7 we start, and it's a neutral pH. If we take to the right side, we will increase basicity, meaning it will be more alkaline, and for the left side towards 0, it will be increasing the acidity. And you have here this equation for the pH equal to the minus logarithm hydronium ion, that means the pH value. pH of common substances, you should take a look for this scale, and you should know also the most important values for pH for daily using food or dietary or nutrient. If we take from the 7, pure water at 25 Celsius, less than 7 it will be milk, 5 it will be black coffee, tomato and wine at 4 and 3 and half, vinegar less than 3, lemon juice 2, stomach fluid around 1 or less, battery acid will be 0 and very strong acid here. And for the right side, more than neutral, you have blood, seawater, sodium bicarb, borax solution, milk of magnesium, detergent, aqueous ammonia 11, bleach 12, and 14, 1 molar NaOH. It will be very strong base in this scale. We have some example here. pH and salt over acid ratio. Okay, what is the molar ratio? This example is available on the book, textbook, what we call Martin in physical pharmacy, talking about the calculation of pH and salt over acid ratio. So if we start with this example, what is the molar ratio salt over acid required to prepare an acetate buffer of pH 5? Also express the result in mole percent. So if we take a look here, we see we have the pH, the pKa for acetic acid 4.76 plus log salt over acid. So we want this ratio, log salt over acid equal to the pH minus pKa. It will be 0.24, and log it will be 1.74. Therefore, the mole ratio of salt to acid will be 1.74 over 1. This is the ratio. Mole percent is mole fraction multiplied by the 100. يعني راح نضرب احنا النتيجة في 100 حتى نطلع المول fraction. The mole fraction of salt in the salt acid mixture is equal to this and equal to 0.635, and in mole percent the result will be 63.5%. You will take two levels. The first level 1.74 over 1, and you will take the equal lower unit till you get this ratio 0.635 and multiply by 100% will be 63, the total ratio. Using this is another example using the buffer equation. What is the pH of solution containing 0.1 mole of ephedrine? We repeat this example in the previous page, but here as I'm showing you now, it's available also in textbook, the same example, but there I explain it in more details to show how you get the pKa. We have another example here. Calculate pH, what we call indicator. An indicator, what it is methyl rate, is present in its ionic form, IN indicator, in a concentration of 3.2 multiplied 10 to the power 3 molar, and in its molar form it will be H indicator in an aqueous solution at 25 Celsius in a concentration of 6.78 multiplied 10 to the power 3 molar. From the table, we have a table in the book regarding the pK indicator equal to 5.1 is observed from the methyl rate. What's the pH? So we have the pKa in this equation 5.1 plus log this what we call it acid over concentration of salt, and you will get the pH of 4.77. If you take a look for the first level 3.25, this is the concentration of salt, and the concentration of acid HIN In, what we call the indicator, and H for the acid, equal to 6.78 multiplied by 10 minus 3, and the result will be pH 4.77. Now we start with another topic, what we call buffer capacity. Let's define what's the meaning of buffer. A buffer counteracts the change in pH of a solution upon the addition of a strong acid or strong base or other agents that tend to alter the hydrogen ion concentration. In another way, if we have a compound, or a mixture, upon the addition of a small quantity of strong acid or base, it will be a change in a buffer value, and this is what we call the buffer capacity. Buffer capacity beta, what we call the buffer efficiency, buffer index, or buffer value, is the resistance of a buffer to pH changes upon the addition of strong acid or base. Define the ratio of amount added to strong base or acid to small change in pH brought about this addition. This is another definition. We can say it in different ways, but finally we have this equation that represents the buffer capacity in beta equal to change in buffer over change in pH. Delta B, the small addition of gram equivalent per liter of strong base to the buffer solution to produce a pH change. Delta pH, change in pH. We have here the buffer capacity of a solution has a value of 1. When the addition of 1 gram equivalent of strong base or acid to 1 liter of buffer solution results in a change of pH in 1 unit. I will show now in this example. It will be more reliable to understand the change in pH. If we have a state buffer, acetic acid and sodium acetate, 0.1 mole each in 1 liter of solution. That's mean number A, 0.01 mole portion of sodium hydroxide is added. Take a look here for this equation. We will add 0.01 sodium hydroxide here in this equation to the acetic acid. So it will be decreases from the salt formed because we have here sodium hydroxide will be added due to the common ion available on this side for sodium acetate, and will be decreased from here the AC by 0.1 from the equation. If we say it in another way, the acetic acid, when dissociate, the sodium will take more AC from the solution to combine with it and form NaAC, sodium acetate. So for the sodium, we'll add the 0.01, and from the acid it will be decreased by 0.1. The concentration of sodium acetate, the salt, in buffer equation increases by 0.01 as I said, and the concentration of acetic acid will be decreased by 0.01. يعني احنا عندنا الإضافة مال صوديوم هيدروكسيد راح تأثر هذا المحلول اللي موجود بالأسيتيك أسيد راح تقلل الجانب الرياكتنت للأسيتيك أسيد بقيمة 0.01 وتزيد قيمة السالت formed by 0.01 because each addition of base convert 0.01 mole of acetic acid into the 0.01 mole of sodium acetate according to the reaction. Before the addition of the first portion of sodium hydroxide, let's calculate and compare the results before and after the addition of sodium hydroxide to the solution. A pKa equal to pH minus log acid over base over salt, sorry, and we arrange it in this manner. pH equal to the pKa minus log salt over acid should be like here. The pKa after arranging it will be pH equal to the pKa plus log salt over acid. The pH equal to the pKa 4.76 plus log 0.01 for acid and salt, and it will be equal, but upon the change by addition due to the addition of small quantity of strong base, there is a change in concentration of salt and the acid by the addition of strong acid, sodium hydroxide. See here, for the salt you will add 0.01 and for the acid will decrease by 0.01. Taking the calculation, the buffer capacity is not a fixed value for a given buffer system, but depends on the amount of bases added. With the addition of more sodium hydroxide, the buffer capacity decreases rapidly, and when sufficient base has been added, the acid converts completely into the sodium ion and acetate ion. That means when you increase the concentration of sodium hydroxide, the value of buffer capacity will be decreased. And how much you add more sodium hydroxide, the reaction will be shift completely to the right direction, and all the acid will be converted to the salt and conjugated. The buffer has its greater capacity before any base is added, where the salt and acid equal to 1, and according to the equation, pH equal to the pKa. This is what we call the greatest capacity or buffer capacity when the salt and acid are equal. The buffer capacity is insufficient is influenced by an increase in total concentration of the buffer constituent, since a greater concentration of salt and acid provide a greater alkaline and acid reverse. We have this table that explains the buffer capacity of a solution containing equimolar concentration of salt and acid. We can take a look on the left side of number of moles of sodium hydroxide increases 0.01, 0.02, 0.03, and we take a look in the middle table line column. The pH will be increases by the increasing of molar concentration of sodium hydroxide. And by the way, you will see the buffer capacity will be decreases. This you can use it in the application of some example, and you can practice in the calculation of buffer capacity. Another topic we have here, buffer capacity or exact equation. Koppel and Spiro and Van Skyl develop a more exact equation for calculating the buffer capacity. This is the more accurate and more exact equation. Buffer capacity equal to 0.23 concentration, a total concentration that we mean Ka multiplied by hydronium ion over the Ka plus hydronium ion to the power 2. C is the total concentration of buffer, the sum of molar concentration of acid and salt. This equation allows the calculation of buffer capacity at any pH, even when no acid or base has been added to the buffer. Means this equation, it will be benefit in calculating the buffer capacity without adding any amount of base. The equation shows that an increase in concentration of buffer component C result in a greater buffer capacity. Means this C, when it will be increases, result in greater buffer capacity beta. You will check some example here in the next pages and we understand this equation more. We have here this example, buffer capacity and pH. Prepare a buffer solution of pH 5 having a capacity of 0.02. The steps in the solution of problem as follows. Choose a weak acid having a pKa of acetic acid 4.76 is suitable for this case. The ratio of salt to acid as we calculated in the previous equation or example, it will be 1.74 over 1. And we can apply now on this equation. We have the buffer capacity 0.02 equal to 2.3 total concentration we should take. And here we have the concentration of acid multiplied by hydronium ion and concentration of acid plus hydronium ion to the power 2. And you will get the buffer capacity concentration from the buffer capacity. It's equal to 3.75 maximum concentration. This is the total concentration. Multiply 10 to the power minus 2 molar per liter. Finally, from equation B, salt equal to 1.74 multiply acid, and from C, this equation, you will get this ratio by substituting the knowing value here for acid 1.37. Just you take a paper and rewrite the equation in correct manner and practice, you will get the same result. You have acid 1.37 and salt 1.74 because this value equal to 3.7. So you will get by decreasing the number of weight or grams moles of acid from the salt, you will get 0.238. This is for the salt and this is for the acid. By other way, if you now add one of them 2.38 and 1.74, you will get this value for total concentration that's equal to 3.75. Next, add a hydrogen ion concentration of 1.75 multiplied by 5 to the 10 to the power 5. What is the capacity of buffer? This is the same example, but if we have now the buffer capacity unknown and we have the concentration known, you will rearrange the equation by adding the concentration of acid and salt together and you will get the C. See the total concentration for both, because as we said here, hydrogen ion concentration 1.57 containing 0.1 mole of each acetic acid, and sodium acetate will be 0.2. We put it here in equation 2.3 multiplied by 2, and you have this knowing value for Ka hydronium ion. Arrange, multiply, and add, you will get the buffer capacity that equal to 0.115 mole per liter. You can practice with this example and take a look in as a previous equation and example, and you see it's very easy. There is another term we have to know today. It's maximum buffer capacity occurs where pH equal to pKa, or an equivalent term where pH equal to the pKa or hydronium ion equal to the Ka. Maximum buffer capacity equal to 0.576 multiplied by concentration, where C is the total buffer concentration. You can see here on this graph, you have buffer capacity increases with around 4.9 or 5. It represents the total, the maximum buffer capacity for buffer solution for weak acid in pKa 4.76. Here's an example regarding this topic, maximum buffer capacity. What's the maximum buffer capacity of an acetate buffer with a total concentration of 0.02 mole per liter? So we have this equation, maximum buffer capacity equal to 0.576 multiplied by 0.02. You will get this ratio of buffer capacity, 0.01152 or 0.012. Key concept we have here, buffer capacity. The buffer capacity depends on a value. Means number one, on the value of ratio salt to acid, increasing as the ratio approaches unity. Number B, the magnitude of individual concentration of buffer component. The buffer becoming more efficient as the salt and acid concentration are increased. In another way, buffer capacity, as we said, depends on the ratio and the magnitude of individual concentration of buffer component will be more efficient for the buffer becoming increasing by the increase in the concentration of salt and acid. We have buffer in biological system. Means any drug you want to prepare, you should look at the buffer of that system or that site of action, and we should formulate any drug regarding to the buffer of that targeting site to avoid the irritation or indissociation or absorption or metabolism or any other pharmacokinetic and dynamic factors that affecting the formulating of a drug in a specific dosage form. So the pH of tea, for example, we have from 7 to 8. So it's not possible to formulate a drug or eye drops or Accusat or any other dosage form that applied into the eyes by using a pH value more or less than this range. So the pH of blood is maintained at approximately 7.4 by buffer component in the plasma. We have bicarbonate and phosphate buffer. Also, we have erythrocyte buffer for hemoglobin and phosphate buffer too. This is the name for the phosphate and bicarbonate and hemoglobin, oxyhemoglobin. In short manner, we have pharmaceutical buffer that solutions are widely used in adjust pH of aqueous pharmaceutical solution to ensure the tissue irritation prevention optimum therapeutic effect, maximum drug stability, and solubility. And there are many other factors and reasons to maintaining the buffer of pharmaceutical dosage form. Pharmaceutical buffer in tissue irritation prevention means the solution to be applied to delicate tissue or administered parenterally are liable to cause irritation and their pH is greatly different from the normal pH of relevant blood fluid. That means we have some site if we want to formulate a drug or administer it to a given patient, we should take in account the pH for that route. Means if we want to give parenteral uh, drug parenterally, we should know the pH for the plasma should not be formulated more or less than uh, neutral pH or isotonic solution that may cause some irritation or toxicity in addition to decreased therapeutic activity and some adverse effects that affect the patient while using such medicine to be used in parenteral or even in ophthalmic preparation. In case there is a large difference in pH, tissue irritation can be minimized if the volume and buffer capacity of solution is lower than the volume and buffer capacity of physiological fluid. So we have a term of physiological fluid. We should take in account this term and any drug to be formulated and manufactured should follow a certain pH value for each part of the human body. Now we have maximum therapeutic effect versus stability. This is another topic. Means the unassociated form of a weak acid or base drug often has higher therapeutic activity because if we talk about the penetration of drug through the semi-permeable membrane uh, or cell wall of the human body or for any tissue, it will be in an ionized form. Otherwise, the lipid solubility will be control the penetration of drug molecule through this wall, and thereby it will affect the distribution and absorption of a given drug. The pH of maximum stability of a drug for ophthalmic, for example, use may be far below the optimum physiological pH. Under such condition, the solution of a drug can be buffered at a low buffer capacity and at pH that is between the optimum stability. So we should control the optimum stability for the drug and the suitable pH to be administered of a drug at a given site of action. Means we cannot formulate a drug in acidic pH and we administer this medicine or this dosage form in the nose or in the eye because it will cause irritation and does not exert any therapeutic effect.